even on the linear algebra side with inner products and looking at different kinds of norm or length-like measure that you can define when you've got various inner products. Okay, so we'll connect back to some of those linear algebra ideas shortly. Okay, but first, if we look on the notes of page 66, there's a little argument that's laid out here in chapter 3.5, and it's a wrong argument. It's a wrong argument to introduce what we're going to talk about today. So let's have a look at it. Well, it deals with the Fourier series for the function f of x equals x. So that's an example that we worked out together a few lectures ago, I think in the 2 lectures ago. So this function f of x equal to x over the range minus pi to pi. So it's just the straight line of slope 1 across the interval minus pi to pi, straight line through the origin. Well, it has this Fourier series here. Of course, f of x equal to x is an odd function. So from what we know about odd and even functions, an odd function, it won't have any cosines in it. It will only feature sines. So the Fourier series just has this one infinite summation here, which is sine functions. And you've got all the sine nx's, and the coefficient is an alternating 1 over n. Okay. It's minus 1 to the power n plus 1 over n. And 2 times all of that. So actually the Fourier coefficients are plus or minus 2 over n, accordingly. So this is what it looks like here. Now what we're going to do is, well, we've got that equation there. So x, this quantity, is equal to this infinite series here. What happens if we differentiate it on both sides? Okay. Well, we all know what the derivative of x is. The derivative of x is just 1. That's fairly easy to get on the left-hand side. And then what we'll do is we'll differentiate the right-hand side term by term. Because we know differentiation is a linear operator. So here we've got a big sum of different functions on the right-hand side. We'll differentiate them one by one and add all their derivatives together. So each of these sine functions differentiates to the corresponding cosine function. But because the argument is nx, for each of these sine functions, you get n times the corresponding cosine function, cosine of nx. So the n at the front will cancel out these coefficients, 1, a half, a third, a quarter, and so on. So what we get then is that 1 on the left-hand side is equal to 2 times this alternating series of cosines. Now this is an equation amongst functions. You've got the constant function 1 on the left-hand side and this infinite series of cosines on the right-hand side. So if we just look at one particular value of it, we just evaluate this equation now at x equals 0. Okay, we've still got the function, the constant 1 on the left-hand side. On the right-hand side, well, you'll have cosine of 0, cosine of 2 times 0, cosine of 3 times 0, etc. Well, those are all just cosine of 0, and cosine of 0 is 1. So what we get on the right-hand side is 1 minus 1 plus 1 minus 1 plus 1 minus 1. And then we just stop and look at what we have. We've got an equation which says that 1 is equal to 2 times 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, and that goes on without end. Well, okay, I've said in the notes here, that's plainly nonsense. Okay? On the one hand, you've got a constant on the left-hand side, and you've got a divergent series on the other side. A constant can never be equal to a divergent series. Okay? This series, the part in the brackets is alternating between, if you look at the finite partial sums of it, it's alternating between 1 and 0. 1, minus 1, 0. Plus 1, get to 1. Minus 1, you get to 0. So it's not converging. There is maybe a suggestion or a suspicion maybe you could make sense out of it, in that this alternating sum is alternating between the part inside the brackets is alternating between 1 and 0, so you may be tempted to say it has average value a half, and then 2 times a half is indeed equal to 1. But you know, to properly make sense of that kind of talk is quite hard, and you'd have to introduce a lot of other concepts around convergence to do that. So what this example shows is, well, it's maybe a little bit of a paradox. What's going on here? Well, hopefully we made a mistake in that argument, okay? Because we shouldn't be able to reach paradoxical or incorrect statements from true statements. So there must be something wrong in our argument. And where the argument went wrong was when I differentiated both sides of the equation. Okay? Well, there's nothing wrong with differentiating both sides of the equation, but it's how I worked out the derivative of the right-hand side. What I did was I was faced with taking the derivative of an infinite sum, and I proceeded by taking the infinite sum of the individual derivatives. It's that step that's called into question. Okay, so we're just going to do a little bit of further discussion about that now, and then we'll be able to consider that result of Parseval's theorem in the notes. Okay, so let's switch to the overhead now. So what's so wrong about differentiating an infinite sum term by term? So, well, first of all, we'll recall that the differentiation is linear. In that, if I want to differentiate a sum of two functions, f1 plus f2, as long as they have derivatives, I'm perfectly right in saying that the derivative of the sum is the sum of the individual derivatives, right? It's a fundamental property of the operation of differentiation. Integration has a similar property. Integration is also linear, and it's something we use all over the place without thinking most of the time. Okay, so it is indeed linear, and this can be extended without difficulty, just by repeated applications. This can be extended by repeated applications to any finite sum. So that if I'm faced with the derivative d dx of some finite sum of functions, f1 up to fn, that is indeed equal to the derivative of each of them added together. So this is perfectly correct. You have to take a derivative of a sum of 1,000,000 functions added together. You can just go ahead and differentiate each one and add all their derivatives together, and then you'll have the derivative of the sum of the functions. But it's not the same thing to extend this to infinite sums. Okay? But we cannot simply assume this will always hold for infinite sums. So if you want to differentiate d dx an infinite sum of functions, is that the same as the infinite sum of the individual derivatives? Well, maybe it is, maybe it isn't. Sometimes it will be, sometimes it won't. So, question mark, and the answer is not always. Well, why is this? Well, it's to do with issues around convergence. Okay? I mean, a finite sum of functions, there's nothing ambiguous or troubling about adding together a finite collection of real valued functions. I mean, if the functions exist and are well defined, and they take values in the real numbers, or they're functions going from the reals to the reals, then adding together any finite amount of them, there's no problem. You're just adding numbers together forming new function rules out of old rules. There's no conceptual problem. However, as soon as you have an infinite collection of functions, even though each one of them might be, nothing suspicious about it, perfectly good function, you cannot just simply say, oh, well, I'll form a new function now, which is the sum of this infinite collection of functions. Okay? Because that infinite sum might not be well defined, because the infinite sum of function values might not converge. Okay? You can't just, flippantly write down infinite sums on the page and pretend that we're talking about well-defined things without justifying. Because sometimes infinite sums converge, sometimes they don't. So the question surrounds this. Okay? So because of issues around convergence, we need to be careful. We need to be careful about how we do this. So if a function f has a Fourier series, then its partial sums, sorry, don't need the apostrophe there. Its partial sums, the partial sums of the Fourier series, which are, let's write them as fm of x. So by that I mean fm of x will be the constant term of the Fourier series, half a naught, will sum up the first m cosines, and will sum up the first m sines. That's the partial sum of the Fourier series. I mean, the real Fourier series, both of these summations go up to infinity. So the nth partial sum, I'll write as m subscript m, fm, its partial sums converge to f as m goes to infinity. Okay, and we write, what do we write? We write things like the limit as m goes to infinity of the sequence of functions fm equals f. We write things like this. But this convergence of a sequence of functions to a limit function, that can happen in more than one way. There's a few different ways that convergence can happen. Okay? So we're going to talk about, in order to understand the result that's coming, I need to explain some terms to you, and those are pointwise convergence and uniform convergence. Okay? This convergence can happen in at least two ways. So speaking just generally about sequences of functions, the first way is pointwise convergence. Now the point that it's talking about here is the argument x to the function. Pointwise convergence is the weakest kind of convergence, and if a sequence of functions converges at all to a limit function, it will always it will always be converging pointwise. It might be converging in a stronger sense. But what is pointwise? Well, pointwise convergence says that at each point x in the relevant domain, the sequence of values fn, or I'll call it fm of x. So if we fix the point x, okay, we're just talking about one particular point x in this domain. At each point, the sequence of values converges to f of x. I mean, that's the kind of thing we understand for what it means for a sequence of functions to converge to the limit function. But what isn't being said here? So that's just the pointwise convergence, and we know what it means for a sequence of values, sequence of numbers to converge to some limit number. Okay, that kind of thing we covered last year in the mathematics fundamentals unit. So pointwise convergence for a sequence of functions just means at each point in the domain, the sequence of function values, fm of x, that sequence of numbers converges to the limit number f of x. But this definition doesn't make any reference to the kind of rates of convergence. It's possible that maybe for some values of x, these sequences are converging very fast to f of x. And for other values, they could be converging very slowly. Okay, so that's the issue. But this says nothing about the rates of convergence. The rates of convergence at different x. This can cause a problem. We've already seen that problem. I pointed it out to you when we looked at some of the initial examples of our Fourier series. And it was to do with the phenomenon of, we called it Gibbs phenomenon. Just to remind you, I'll show you that now on the screen in a moment. We'll go back to that paper in a moment. Yeah, so this was one of the first examples we looked at. This was the Fourier series with the square wave function, or the Heaviside step function, if you like. This is the function. So the original function f is shown in red here. So it just takes the value 0 from the range minus pi to 0, and then it hops up to the value 1. And then the blue oscillating curve is the partial Fourier series sum, the partial sum of the Fourier series for this function, which includes the first 10 terms. So you can see it's doing a pretty good job of agreeing with the function there. And when we up the number of terms, it's getting closer and closer to the original function. However, you can see that it's doing so at different rates at different points in the domain. If x is a point in the middle of either the positive half of the domain or the negative half of the domain, you can see here that you've already got quite good agreement between the partial Fourier series sum and the original function. Okay? The blue function is quite close to the original function in the middle here of the positive domain and the middle of the negative. But as soon as you get close to 0, the agreement is less good. Now if we say, okay, well that's just because it's converging, it hasn't converged yet. If I bump the terms up to 35 terms, okay, now the region of good agreement is closer to 0. But still, when you're very close to 0, the agreement is not so good. You get these large oscillations. These were called Gibbs phenomena. And even if you I mean, just in this particular example, you can only go up as far as 100, just the way I've programmed it. But okay, at 100 terms, okay, for most of the domain, the convergence is all but pretty much exact, to quite a lot of decimal places. But still, when you get very close to 0, you still see very poor convergence. Now, the Fourier, if you're at a point very close to 0, the Fourier series is still converging to the original function. But it's just doing so incredibly slowly. And you'll have to add, so if you fix x at any point very close to 0 here, you'll have to add an awful lot more terms to the Fourier series until you see these large oscillations move away. But the problem is that these large oscillations will always be there. For sure, they'll get squashed tighter and tighter into 0. And in the limit, they'll disappear. But at any particular partial sum, they're always going to be there. Okay. So this is an example. I mean, this is still convergence, but it's pointwise convergence. At each point in the domain, there's some convergence going on, but there's no reference made. There's no reference or no conditions put onto the different rates of convergence at the different points. And you can see here in this example, we've got very different behavior. Fast convergence in the middle of this region here. You can't even see the blue function. The red just completely obscures it. Fast convergence in here, but very bad slow convergence at points very close to 0. And the closer to 0 you get, the worse the rate of convergence is. And it's at functions like it's at situations like that where you cannot do the or you're not allowed to do the term by term differentiation. So, see the square wave example. Square wave function example. That's what we were just looking at. So, differentiating term by term here is not justified by pointwise convergence alone. You need something stronger. Formally, pointwise convergence, see, remember convergence ultimately, you'll remember from last year, convergence is expressed formally using the concept of epsilon values and arbitrary small epsilon and in terms of distance from the sequence terms of the limit. So it's useful to look at what the formal logical version of pointwise convergence is. Formally, pointwise convergence of sequence fm to f is written. It's written as, well, for every x in the domain, so for every x in the domain, for every epsilon greater than 0, there will exist a point capital M such that for all little m greater than or equal to capital M, the absolute value of fm of x minus f of x is less than epsilon. And why have I bothered to show you this? Well, because for the next type of convergence, the much stronger, better kind of convergence, if you like, that we're about to look at, which is called uniform convergence. Uniform convergence is just about changing the order of these quantifiers. So this statement, when you read it left to right, it's saying for every x in the domain and for every epsilon. Now epsilon is the kind of measure of the closeness of agreement between fm of x and f of x. For every x in the domain, for every tightness of agreement, if you like, there will exist a point in the sequence of functions such that at every point after that point, capital M, the distance between fm of x and f of x is less than epsilon. But what's allowed by this is we don't have to have, in order for this statement to be satisfied, we don't have to use the same capital M for every x. Okay? Because it's just saying for every x there will exist an m. Well, for different x's you could have very different m's. Okay? So for some x's you might see this inequality being satisfied very early on for a relatively low value of capital M, like the ones in the middle of the interval in the square wave function we were just looking at. But for other values of x, you might have to take an extremely large value of m before you see this level of agreement between fm of x and f of x. That would be the case for those points very close to 0 in the square wave example we were just looking at. Well, so one way you can get rid of this, different rates at different values of x, is just to simply take this exist m statement and change its position for all x. Because if in first we say that there exists an m such that for every x in the domain this agreement happens after capital M, then you're insisting that the convergence kind of happens at a bounded rate across the whole domain. So you can't have this very good behavior in some locations of the domain, a very bad behavior in other parts of the domain. So we can look at uniform convergence. So uniform convergence of fm to f is where there is a bounded rate of convergence for all points in the domain. And the formal version of it just says for every epsilon greater than 0, there exists a point capital M such that for every x, for all m greater than or equal to capital M, absolute value of fm of x minus f of x is less than epsilon. Now the change looks very innocuous in one way. All I've done is change the position of these quantifiers. So I've taken the universal quantifier for every x in the domain, and I've put that after the existential quantifier that exists m. But that makes all the difference, okay? Because the first version, the pointwise version, says for every x, there will exist some m. But for different x's, you could have very different m's. This version says, well, whatever the level of agreement we're after, so this small value epsilon, which is measuring the distance between fm of x and f of x, there'll exist one point in the sequence of functions. And then we'll see this level of agreement across all points in the domain. Okay. So when you break it down logically, you'll see that it's saying this type of convergence is much more restrictive. It's harder to achieve. It's a stronger type of convergence. So note the relative positions. So the important point is the relative positions of the for all x and the exists m. That's where the difference lies. So this type of convergence is much more restrictive. Or another way of saying that, it's harder to achieve. It's less common. Okay? Any sequence of functions which is converging uniformly is converging pointwise. Okay? But not every sequence of functions that converges pointwise is converging uniformly. Okay? So that example of the square wave function, which we saw before, is a non-uniform convergence. So there's a theorem which basically says if Fm converges to F uniformly, then the derivative of F with respect to x we can write as the limit as m goes to infinity of the derivatives of the individual functions. So the way it's expressed there is take the f is the limit function of the fm. So on the left-hand side, we've got the derivative of a limit. On the right-hand side, we've got the limit of the derivatives. It's that interchange of the two orders. That's what we need uniform convergence for. Isn't necessarily true if you've only got pointwise convergence. Okay, and so this leads us on to, well, first of all, any questions about that, or any point of that that you'd like me to clarify? So, knowing about these different types of convergence, knowing that when we do have this good, better type of convergence, uniform convergence, we are allowed to differentiate term by term. This brings us to this result called the Parseval's theorem. Okay, so maybe I'll just stick it up on the notes. So Parseval's theorem only applies when the Fourier series is converging uniformly to the original function f. Now before that, we've got a result which gives us some conditions, some simpler conditions on the function f, which will guarantee the uniform convergence of the Fourier series. And we won't be proving theorem 3.6. We will prove theorem 3.7, the base on it. So theorem 3.6 says, well, if you want your Fourier series to converge uniformly to f, it's enough to know that f is continuous on the interval, so it doesn't have any discontinuous jumps like the square wave function has. The square wave function has a point of discontinuity at the origin. It jumps from the value 0 straight up to 1 instantaneously. The discontinuous jump. So, but if your function isn't like that, if it is continuous, if its derivative df dx is piecewise continuous, So there's at most a number, you can have some sharp points where the derivative changes instantaneously. And secondly, the function f is genuinely periodic, and that it agrees on the interval. It agrees on the endpoints of the interval. That f of minus pi is equal to f of pi. So its starting value on the interval is the same as its ending value. If those conditions hold, then the convergence will be uniform. So then we have Parseval's theorem. Parseval's theorem is, it's very much, and this is where we connect back to the linear algebra. It's very much talking about the norm of the function, the inner product of the function with itself, and how that relates to the Fourier coefficients. So we've got a function which has this standard Fourier series. We're assuming that the Fourier series converges uniformly to the function f. Then in that case, this integral on the left-hand side, now you recognize this integral on the left-hand side, it's the integral of f of x squared, f of x times itself, over the integral minus pi to pi. That's the standard inner product that we have on this vector space of functions, integrating the product of the two functions across the domain. So this object on the left-hand side you think of as the inner product of the function with itself. We know that there's a way to interpret that. That's the square of the norm of the function f. On the right-hand side, we have this, okay, complicated enough, but nice expression. This expression on the right-hand side is more or less the sum of the squares of the Fourier coefficients. Okay, it isn't quite because, well, yeah, that's the constant coefficient squared. So the constant coefficient is half a0, so square that, you get a quarter a0 squared. And well, because of these confounding multiples on the other side, we have to take a half of the sum of the squares of all the a_n's and the b_n's. Now we'll work through some examples in the next lecture based on this, but so here's a way to think about Parseval's theorem. Compare it with the more familiar situation set up in the vector space R3. The vector space R3 with the orthonormal standard basis. So you got these three basis functions, one with E1, which is 1, 0, 0, E2, which is 0, 1, 0, and the third basis vector E3, 0, 0, 1. So that's your standard orthonormal basis in the vector space R3. Any vector x can be written as a linear combination of E1, E2, and E3. And we can call these the coefficients in the linear combination x1, x2, and x3. And then, we're all very familiar with how to think about the norm of the vector x. The norm or the magnitude, the length of the vector x. What is the length of the vector x in R3? If what we know about x is its standard representation in terms of the orthonormal basis, well, we know that the square of this norm is equal to the dot product of the vector x with itself. And because this is an orthonormal basis, this dot product we're squaring it, so we lose the square root. So it's x1 squared plus x2 squared plus x3 squared. So it's the square of the magnitude, which is the inner product of the vector, which is the dot product of the vector with itself, and that's also the sum of the squares of the coefficients. Well, in Parseval's theorem, we have the analogous statement to this. Okay. Now there are confounding factors in it. So there's that in Parseval's theorem we have a half of the sum of squares of all the a_n's and b_n's. So that messing it up factor, that confounding factor of a half is there because in the way we set up the Fourier series, we didn't work with an exactly orthonormal basis. We were working with an orthogonal basis, ones that the functions were orthogonal to one another, but they weren't all of that magnitude 1. So you're very familiar with this idea. This is nice and straightforward. Basically just Pythagoras' theorem applied a few times. And what we have in Parseval's theorem is the equivalent thing in the infinite dimensional vector space that is the setting for Fourier series. Okay, we come to the end there, but when I see you this afternoon, we'll finish it off by looking at example 3.9, showing some work with one of these, and applying Parseval's theorem, and then I'll finish it off by telling you a little bit about the Fourier transform, which is generalization of Fourier series and something you'll use a lot in the digicoms and sound processing unit in third year, should you choose to do that.